Hello there, this is an Algebra 1 video. It is Chapter 9, Section 3. And today we'll be talking about transformations of quadratic functions. And the first type of transformation we'll be discussing is a vertical translation. And basically what a translation means is exactly that. If you know what the parent graph of what looks like, and this can apply to a lot of different types of functions. It's not just quadratic functions. We also did something similar to this when we learned how to graph absolute value. And as we continue in algebra, you will learn new functions, and these transformations and translations will carry on also in those functions as well. So back to a vertical translation is basically when the graph gets shifted up or down from where its original position is. So the function will look like f of x equals x squared. That's our parent graph, and I've basically got that graphed already. And then you have a plus or minus k value. And so I always talk about how this value is outside of parentheses as opposed to inside of parentheses. And we'll talk about that when we get to the horizontal translation. And you can see what I mean by that. But whenever there's a value that is added to the function or subtracted from the function, then basically if you have a plus k, then they're going to shift the graph k units up. So if it's plus 3, you're going to shift it up 3 units. And so I want to show you what that would look like. If you were going to shift the graph up, it would basically have the same form, but all of the points would just move up. So you would get a parabola that looked something like that. It'd be the same graph, but it would just be shifted up. And if you had a negative k value, then it would shift the graph down. But again, it would be the same looking parabola and graph, but just shifted k units down. Alrighty, so we want to do that here. It says, describe how the graph of each function is related to the graph of f of x equals x squared. So f of x equals x squared being our parent graph. And it's asking us here in part A, x squared plus 3. So describe how the graph of each function is related. Well, this would be a vertical shift of 3 units up because it's positive 3. In the case of part B, because we have a minus 4, it would be a vertical shift of 4 units down. Now notice that this doesn't actually ask us to graph the function. It just says to describe how the graph of each function is related. But you could graph the function very easily. What's nice about transformations is that they are very easy to graph. You don't have to spend all the time that you would spend finding the vertex and all that kind of thing. We know that x squared has 3 main points. When x is 0, y is 0. When x is 1, y is 1, because 1 squared is 1. And when x is negative 1, it's also 1. So this is what your parent graph looks like. And so x squared plus 3 would be shifted 3 units up. So this is 1, 2, and 3. We would shift this point 3 units up, so 1, 2, 3. This point would shift 3 units up, 1, 2, 3. This point would shift 3 units up, 1, 2, 3, and your graph would look like this. And you can tell here that what I've got is x is 1, y is 1, 2, 3, 4. And if we actually test that in the function, you'll notice that 1 squared is 1 and 1 plus 3 is 4, so it actually works out. So you don't actually have to graph it, but you could very easily if you know what the parent graph looks like. So again, 0, 0, 1, 1, negative 1, 1, that's the parent graph. And the x squared minus 4 graph is going to be 4 units down, so you're going to have 1, 2, 3, 4 units down. This point will go 1, 2, 3, 4 units down, and 4 units down, and you get the same graph shifted 4 units down. And that's basically how quick you can graph these functions. So now we'll have you try these, and then we're going to go to a horizontal translation. And now you'll see what I meant by talking about being within the grouping symbols and outside the grouping symbols. You might recall that when we did absolute value, you could have absolute value of x, and then you would have absolute value of x minus 2, and you could have the absolute value of x plus 3. So there's a number in this case outside of the grouping symbols, the grouping symbols in this case being the bars. This is a value inside the grouping symbols, and so something similar to that is happening with the parabola. In the case of the vertical translations, the plus k was not inside of grouping symbols, and this time the plus or minus h is inside the grouping symbols, which in this case happen to be parentheses. So when you have a situation like that, a plus h would mean shifting the graph h units to the left, and so that would look like, here again I have graph, the parent graph. If I was shifting the graph to the left, it means that the graph is going to be this direction, same graph but shifted to the left. And if I have the negative h value, then it's going to shift h units to the right, so that would be same graph but shifted over here. Alright, so that's basically what it would look like. So we want to go to an example, and again it's asking us to describe how the graph of each function is related to the graph of x squared. And because there's a minus 2 in here, based on what we just said earlier, you're going to have a horizontal shift of 2 units to the right. Alright, because we have a minus h value here, so you're going to shift it 2 units to the right. And then in part B, you're going to have a horizontal shift of 1 unit to the left, because you have a plus 1 here. When you have a positive h value, you shift it to the left. So again, you could graph these very easily. Having issues with my pen here. Oh my goodness, I just want a black. Thank you. So again, you usually start, or not usually, but you always start with your parent graph. So there's your parent graph. And because it says to shift it 2 units to the right, all it means is that I'm going to take and go 2 units to the right, so now my graph will be here. In the case of part B, because it says plus 1, we're going to shift it 1 unit to the left, so it would be there. Very easy to graph those. Again, it doesn't ask you to graph it, it only asks you to describe how the graph of each function is related to the original graph, but you could graph it very easily as well. Alright, so we want you to try do-it-yourself number 2, and then we're going to go on to example 3. And it says, describe how the graph of each function is related to the graph of f of x equals x squared. Now this time I'm not going to, well actually I probably will. I'll go ahead and graph them for you. But now what you have is basically 2 things happening. So you have a number inside the grouping symbols and outside the grouping symbols. So because of the number inside the grouping symbols, I'm going to abbreviate at this point. You're going to call that a horizontal shift, 3 units. And because it's a minus 3, we're going to go to the right. But at the same time, you also have a vertical shift of 2 units up because of the plus 2. In the case of part B, you're going to have a horizontal shift of 3 units left because of the plus 3, and you're going to have a vertical shift 1 unit down because of the minus 1. And again, to graph that little guy, your parent graph is right here, and the transformed graph will be 3 units to the right, so I'm going to go 1, 2, 3 units to the right, and 2 units up. 1, 2, so 3 units right, 2 units up, that becomes my vertex instead of over here, and then my parabola is over there. Really easy to graph. Over here, do something very similar. Here's our parent graph, and then we want to go 3 units left, so we're going to go 1, 2, 3, and this time I want to go 1 unit down. So we're going to go 3 units left, 1 unit down, here's my vertex, and then there's your parabola. Easy peasy Japanesey. So now I want you to try these 2, and then we're going to go to dilations. Now dilation is also a type of transformation, But a dilation is when you have a value in front of the x squared. So this is neither a plus or minus anything, and it's not inside grouping symbols. This is when you're multiplying by a scalar, you're multiplying by a number. All right, so that's going to affect what we call the stretch or compression. So basically, if the value of a is larger than 1, like 2x squared, 3x squared, 5x squared, any number that's larger than 1, even 3/2 x squared, because 3 over 2 is 1.5, so it's larger than 1, then you have a vertical stretch. And so what you want to think about there is if you were taking this graph and stretching it this way, what would happen is you would basically see the graph get a lot narrower. So if a was greater than 1, you would have something like this happening for your graph. And then the second part is for the value of a between 0 and 1. So now we're not talking negative, we're just talking between 0 and 1. So we're talking about fractions that are smaller than 1. So basically, if you had 0.3, that's smaller than 1, but bigger than 0. 1/2 is smaller than 1, but bigger than 0. So between 0 and 1, then you would have what they call a vertical compression. And what that means is that instead of stretching it out, imagine if you were like bringing these two together and like compressing it. What would happen is that this graph would kind of like spread out, because if you're pushing down on it, if you imagine this was like a fluid thing, then when you push down, it's going to kind of open up, versus when you pull it up this way, it's going to stretch it. So hope that makes sense. But basically what you end up with is a wider graph. So the salmon color here, the inside, is the vertical stretch, which is a narrower graph. The red is the original, and the green is the vertical compression, which we'll call that, which is a wider graph. All right, so describe how the graph of each function is related to the graph of f of x equals x squared. So we have a 1/2 in front of the x squared this time. So because that a is less than 1, it's going to be a vertical compression by a factor of 1/2, and all right, and then for part B, I was just checking if they wanted us to say by what factor. The book does not actually ask you to say by what factor, but it is by a factor of 1/2. In part B, because you have the 3 here, now you have two things going on. In this case, you only had one thing going on. But here you have a 3, which is larger than 1. So that's going to be a vertical stretch. But you're also going to have a vertical shift. All right, because of the +2, a vertical shift 2 units up. All right, so what we should expect to see in this case is when you graph this function, we're going to start with our original. Our parent graph is right here, y equals x squared. And because it's a compression, the 1/2 is going to make it look a lot wider. So you're going to end up with a graph that looks something like that. In the case of part B, we're going to again start with our parent graph, but we're going to have a vertical stretch of 2 units, vertical shift 2 units up, so we're going to be 2 units up, and on top of that, you're going to be a lot narrower, so you're going to have something that is a little tighter like that, tighter against the y-axis. Alrighty, so now we want you to try these little guys, and then we will go to our reflections. Alrighty, so in the case of a reflection, it's exactly that. A reflection is like when you look in the mirror and you see yourself right back. A reflection in the graph case means that you pick a point of reference and then you basically see a mirror image. So when you have a negative in front of the x squared, it becomes what we call an x-axis reflection, which basically means that you have a mirror image along the x-axis. So this would be what your negative x squared would look like. Also, if you have f of negative x, like this, that would be where the negative is inside of the parentheses like that. If that were to happen, then you would have a y-axis reflection. So if the negative is inside the grouping symbols, then you would have a y-axis reflection. But I will tell you that with the case of the parabola, the y-axis reflection is kind of a moot point, because if you had the parabola is already symmetric with respect to the y-axis, so if you were, it's already a mirror image of itself on that y-axis. So that's not really going to affect much in the case of a parabola. But the x-axis reflection for sure is what makes the graph flip upside down. All right, so here we have, describe how the graph of each function is related to the graph of f of x equals x squared. And so we have a negative, so we're going to definitely have an x-axis reflection. We have a 2, which is greater than 1, so that's going to be a vertical compression, vertical stretch by a factor of 2. And you're also going to have a vertical shift 3 units down because of the -3. So we're going to end up, I'm going to go ahead and graph this really quickly for you. Again, we want to start with our parent graph. And there we go. And then we have an x-axis reflection that will be upside down, a vertical stretch, and shifted 3 units down. So we want to go 1, 2, 3, shifted 3 units down. So we're going to have a vertex here. And instead of it opening up, it's going to open down. But not only that, a vertical stretch is going to be a lot tighter to the y-axis. So it would normally be like this. We're going to be on the inside. So it's nice and skinny. And of course, I don't have much space, but you want to make it right there. We can close this real quick. And you can kind of see here, you want this to be nice and skinny there, but 3 units down and upside down. Alrighty, so we want to come back over here for part B. We're going to have, again, our parent graph right here. And in this case, again, we're going to have an x-axis reflection. We're going to have a horizontal shift 2 units to the left because of the +2, and then a vertical shift 1 unit up because of the +1 there. So that means that we're going to be two units left, so we're going to go 1, 2 units left. We're going to go 1 unit up, so this is going to be my vertex right there. And because of the x-axis reflection, we're going to be upside down. And the -4 is going to make it very skinny. I didn't put that on here, but we also have a vertical stretch as well. Vertical, okay, my pen is having issues. Vertical stretch as well because of the 4 here. So we're going to have our graph be very skinny. All right, so it's not going to be as wide as this one's going to be skinnier. It's going to be upside down to the -4, 2 units to the left because of the +2, and 1 unit up because of the +1. So there you go. So now we're going to have you try these, and then we're going to go to examples. This is actually kind of a, it's not a trick question, but it's, oopsie daisy. I want to bring back my strip down here. Sorry about that. And here we go. So in this case, it's a multiple choice question. It says, which is an equation for the function shown in the graph? And so what we can see from the graph is that it's upside down. And because it's upside down, we know that the a value has to be negative. So right away, we can rule out any positive a value. So this positive 1/2 x squared, not going to happen because it's upside down. It's also not going to be d because it's also positive. So that eliminates a and d options. So now we have b and c. And the other thing we can see from the graph is that it is shifted 5 units up. 1, 2, 3, 4, 5. That means that it should have a k value of +5. And since this has a -5, it's not going to be b. And so therefore, our answer is C. Alrighty, so now we're going to ask you to do this little guy. And it's a little bit backwards, but we're looking for the graph of negative 3x squared plus 1. So we're looking for a graph that has a vertical shift of 1 unit up, and it should be upside down, and it should have a stretch factor. It should be skinnier than the normal graph. But you can decide there. And if you want to see better graphs, you can do so on page 567 of your textbook. I did my best to draw them, but if you can't make out what they say or what they are, you can definitely look in the textbook. And then we have our last example, and this is where we officially now talk about vertex form. And vertex form, you can see, is where you'll see the A value that we talked about, which is pretty much in charge of reflections and dilations, whether it's a vertical stretch or a vertical compression. We have the H factor, which is going to affect the horizontal shift. And we have the K factor, which is going to affect the vertical shift. And so that's what we call vertex form. And so in example 7, it says, during a fireworks show, the height h in meters of a specific rocket after t seconds can be modeled by h of t equals negative 4.6 times t minus 3 quantity squared plus 75. Graph the function. And then how is it related to the graph of f of x equals x squared? Now we've done a lot of graphing already. This graph should, so I'm not going to graph it in the interest of time, but I am going to go through the how is it related part. So we know that there's a negative. So because of that, the graph should definitely be upside down, which is an x-axis reflection. And then we know that because of the minus 3 that's inside the grouping symbols, that's the horizontal shift. And that's going to be 3 units to the right because it's a minus 3. I also should mention the 4.6 means that we're going to have, 4.6 is larger than 1, so you're going to have a vertical stretch. And then lastly, we have the 75. The plus 75 is going to be a vertical shift of 75 units up. So when you do graph this function, it should be shifted 75 units up. So the vertex of the graph should be at 75 on the y-axis. The horizontal shift should be shifted 3 units to the right. A vertical stretch means it should be a lot skinnier than the original x squared graph. And it should be upside down with the x-axis reflection. So now we're going to ask you to do this do-it-yourself question, and once you have completed this do-it-yourself question, you will have completed your notes for this lesson, and I will see you in class, and thanks for watching.